top of the curve. That means we're corresponding to the value for p, which is the highest, because the highest value would be the top of the curve. So what we do is we want to write down the expression for the likelihood, p raised to the 4th power, 1 minus p raised to the 6th power. Take a derivative of this function with respect to p, set that derivative equal to 0, and solve to see what value for p gives me a 0 value for this derivative. Well, the mathematics is easier if we look not at the value for the likelihood, but the value for the log likelihood. Because the number that maximizes L also be the number that maximizes the log of L. Well, if you take the derivative, well, first, if you write down the expression for the log of the likelihood, if this is the likelihood, the laws of logarithms, and we won't go through this today, turns out to equal 4 times the log of p plus 6 times the log of 1 minus p. The log of a product, remember, is the sum of the pieces that make up that product, and all we have here is we've taken this one expression, p to the 4th times 1 minus p to the 6th. You take the log, it's the log of p to the 4th, plus the log of 1 minus p to the 6th. That's the same as 4 times log p plus 6 times log 1 minus p. If you don't remember this, believe me, it's one of the laws of logarithms. But we want to take the derivative of this expression with respect to p. If you've had some calculus and you want to remember it, it turns out to equal in the following expression. 4 divided by p minus 6 over 1 minus p. You could write that as one fraction. 4 times 1 minus p minus 6 times p divided by p divided by 1 minus p. Give me a value of 0 for this expression. Well, this is a quotient. The numerator is 4 times 1 minus p minus 6p. Denominator is p times 1 minus p. The whole quotient will be equal to 0 when the numerator is 0. So the value for p, which makes this derivative equal to 0, the value for p, which makes the numerator 4 times 1 minus p minus 6 times p equal to 0. I'll solve this expression for p. Put all the p's on one side and all the pure numbers on the other. We solve for p. We get the number 0.4, meaning the maximum likelihood estimate for this coin, for the coin having a probability of heads, the value for p, the maximum likelihood estimate for that number 10 times and got 4 heads. If you flipped it 6 times and got 10 times and got 6 heads, the maximum likelihood estimate would be 6 over 10. If you flipped it 10 times and got 2 heads, the maximum likelihood estimate would be 2 divided by 10. So this is what a maximum likelihood estimate is. It's the estimate for the unknown risk p, which best explains what the data showed. The data showed you've got 4 heads and 6 tails. And it matches maybe your intuition. If I gave you a coin, I didn't tell you whether it's a fair coin, but you flipped it 10 times and you got 4 heads, you would estimate that the risk that the next time you flip it would come up heads would be 4 out of 10. Well, that's essentially what's happening when you fit logistic regression models with SAS or with any other software package. We say that a person's risk of getting disease, like a coin's risk of showing a heads when you flip it, is specified by this equation. It says your log odds getting disease is equal to B0 plus B1 times X. Remember, X in the previous example was the person's gender. Coded 1 if you're a male and 0 if you're a female. This model says your log odds of getting disease depends on your gender. Another way of solving this equation, it says log odds of disease is equal to B0 plus B1 times X, is to say a person's risk is equal to e to the b0 plus b1 times x over 1 plus e to the b0 plus b1 times x. What this model is telling you is that there are 2 risks, one for men and one for women. If you are a male or a female, your risk of getting disease is equal to e to the b0 plus b1 times x plus 1 over that same expression. If you are a male, your value for x is 1, so your expression becomes e to the b0 plus b1 over 1 plus e to the b0 plus b1. If you're a female, your value for x is 0. Your model says your risk is e to the b0 over 1 plus e to the b0 because the b1 times x1 term disappears. So the model allows you to have two different risks of getting disease, one for a male and one for a female. Likewise, the model says there are two risks of not getting disease, which is just 1 minus the risk of getting disease. And mathematically, that can be re-expressed as a function of B0 and B1 and your sex status. So just like before, we can write down the probability of seeing what we actually saw in a study. We did a study, we followed a bunch of men and a bunch of women, 1,363 men and women for 18 years. Some of the people got disease, some of the people didn't get disease. So let's write down a probability, a bunch of p's multiplied by a bunch of 1 minus p's. And this is just a mathematical equation to write down the long sequence of p's times 1 minus p's. Just like if we go back a few slides, and we looked at the coin flips. We had 10 coins, the first coin showing a head. You've got 1,363 people. Go back to that 2 by 2 table. (1,363 people). 268 of them got disease. 1,095 did not get a disease. So let's write down the probability of getting 1,363 people, of which 268 of them get disease, and 1,095 don't. For everybody who got disease, we want to write down the risk of getting disease, P. For everybody who didn't get disease, we're going to write down 1 minus P. So just like in the coin flip, we're going to have a big, long sequence of P's multiplied by 1 minus P's. But there's now going to be 1,363 of these expressions. 268 of them, I guess it was, if I go back to the slide. 268 of them were P's, and the other 1,000 were 1 minus P's. But now the model says your value for P and your value for 1 minus P also depend whether you're a male or a female. It depends on these x's. What that means is this expression here, this first symbol, which looks like it's a Greek letter pi, means I'm going to be multiplying a bunch of things. I'm either going to be multiplying P or 1 minus P. I'm going to do this 1,363 times. This expression, P raised to the y power times 1 minus P raised to the 1 minus y power, y is the outcome of the person. Y equals 1 means they got disease. Y equals 0 means they didn't get disease. So if a person got disease, y is 1. 1 minus y is 0. Any number raised to the 0 power is equal to 1. So anybody who gets disease, this expression is just P. Anybody who didn't get disease, y is 0. This first expression is just y raised to the 0 power, which is 1 times 1 minus p raised to the 1 minus 0, which is 1, becomes 1 minus p. So this expression in the previous slide, all it stands for mathematically is 1,363 p's and 1 minus p's being multiplied together. 268 of them are p's, the other 1,000 and some odd are 1 minus p's. There's 268 people got disease and 1,000 people didn't get disease. But now, these p's and 1 minus p's depend on the value for x. Because x determines whether your risk is going to be of getting disease. Your p is either going to be this expression, e to the b0 plus b1 over 1 plus e to the b0 plus b1. Or if you're a female, it says your risk of getting disease is e to the b0 over 1 plus e to the b0. So males and females have different risks from this model. But what's going to happen is the model is going to be fit to a data set using maximum likelihood estimation. We're going to come up with the best value for B0 and the best value for B1 to explain what actually happened. Why did these people, these men, get disease and these other men not get disease? And why did these women get disease and these other women not get disease? That's what the B0 and B1 are going to try to do. Let's explain why some people got disease and other people didn't get disease. So here's what the computer is going to be doing for you. You don't have to do this by hand. It's going to give you estimates for B0 and B1, the best estimates it can come up with. Try to explain why some people got disease and other people didn't.